Hi everyone. In the section 2, we need to debate it to what the designing FIR filter. Okay, we need to talk about it. First of all, we need to say that the FIR filter has different process to design or designed from IIR1. Okay, since we have temporal or the windowed in the technical name, windowed signal pattern in here, because we have only feed-forward terms to be collected from the input signals. Okay, and so we need to apply the windowed signal or the windowed pattern to analyze this signal or the filter these signals. Okay, in order to design for filter, we must tell about to what the sync function, which means that this is written as to what the sync t is equals to the what the sinus pi t divided by pi t. This is a continuous one. Okay, in the digital domain we have this signal just like this one. The n is the discrete domain or the index of the R samples, and sin pi times n divided by pi times n. This is the discrete one. Okay, and so this signal is summarized in the theorem 8.1. The sync function is defined as, from from these definitions, the sync t, which is equals to the sin pi t divided by pi t, until the t not equals to 0, but otherwise the t is equals to 0, we have the 1. And so we can create this kind of signals in here. This is a rectangular pattern or the any in this in the in the real plane. Okay, and so this is the R theorem. And so what's the purpose of using this function? This function creates a window to be utilized in your in your filter design. And so, for example, up to 1 to 10 the signals may be processed with with this pattern based on the FIR filter coefficients, because we have the only open loop response or only the input response in here, not the feedback one. Okay, this formula is coming from the inverse Fourier transform, guys, and so we need to prove that. Firstly, in order to understand the importance of this function, first of all, the proof can be given by the 8.1. Okay, firstly, assume that the rectangle frequency range pattern like this one. First of all, just remember the body plot, the f and we have also a magnitude. For the ideal filter, we need to set these values into the what, into the 1. But in terms of the what, the minus pi to pi, right? In the earlier identity, we have the what, the two imaginary components at the what, the real and imaginary plane. For example, if we have the J1 or J2, and also we have the complex conjugate formula, like the minus J1 minus J2. And so these patterns is similar just like this one, but we don't have any information about these terms. This is what the symmetry of this algorithm, and so we need to always use this pattern in here. And so this is the representation of the ideal low pass filter, right? Just remember that before the pi we have the magnitude of the 1, and so after the pi we have the 0 magnitude in here. Okay, and then if we take the inverse Fourier transform in here, or this signal, it creates to the what, to this pattern, the ft which is equals to what, the minus pi to pi and 1 e j w t dt, and also this is equals to minus pi to pi. Okay, and so this pi to minus pi is coming from the what, the earlier identity formulations. Okay, this is simple. Pi minus pi, this is the pi, this is the minus pi. Okay, and so we cover the whole regions in here, and so this is written as the j dot t times e over jw t in here, just like this one. And so this is simple as the what, the jt times e j pi t minus e minus j pi t. This is the representation of the what. These terms can be given in here, just like this one. 2 divided by 2 times 1 j_t times e j pi t minus e minus j pi t, which is equals to the what at this place, which is equals to 2 divided by t times 1 divided by 2 j e j pi t minus e minus j pi t, and also this is equals to what, the sinus pi t. Okay, and so this yields us to what, to 2 divided by t times sinus pi t. Okay, this is the R inverse transformation of these coefficients. Okay, and so if we only have the what, the half of the band in here, and so this formula is going to do what, is going to do sinus pi t divided by t. And if we normalize the R signal, because we have the pi in here, if we normalize this signal, and so we need to divide the pi values in here, and so pi divided by pi, which is equals to 1, and so this is the normalized frequency for a given cutoff one, right? And so this formula returns or turn into the what, these formations. Okay, and so this is our windowed function, which is coming from the what, the body plot of the magnitude and the f, which is based on the what, the earlier identity formulation in here. And so this creation is normalized with the what, with the pi values of these terms. Okay, so if we have this function, we can apply this function on another signal in time domain, right? Because if we have this information coming from the frequency patterns, and so we can discretize it, and so we can multiply this signal with the what? With another signal to filter to any process or to suppress the noises or the something like that. Okay, and so this represents to the what? The magnitude and f, and also this is the 1 and this is the 1. Okay. This is so simple. So this is a windowed function, but we have another windowed function, because if we convolve any signal based on this sinc theorem or the sinc function, and then we can get what ideal low pass filter design. But in the real life application we have the non-linear responses or some non-ideal cases. Okay, so in order to remove these effects or the sinc function is applied with window function, which is corrects our cases or our inputs in a non-ideal cases. And so the reason is that due to the prevent the losing informations in here from the signal. And so what's the case of these terms? Firstly, the ideal signal is represented with a rectangular window in here, which means that Wn is equalized to the what? To the 1. And so the n can be chosen as to what? To -5 to 5. Okay. In the Hamming window, this is a curvature window, which is equals to the what? The Wn function 0.54 0.46 times cosinus 2 pi n divided by greater than 1. Okay, this is like the curvature of these terms. Okay, or the hand window may be applied in here, just like this one, Wn, which is equals to the what? The 0.5 times 1 minus cosinus 2 pi n divided by n greater than 1. Okay, and so we have also a Blackman and the Kaiser windows in here, but these signals in real life creates to what? To this kind of signals. For example, this is the sample points, sample data indices in here, and also we can give the what? This is the magnitude or the amplitude of the R signal, which is equals to 1. In the rectangle window we have the what? This kind of information. But in the Hamming window we have the what? This kind of pattern to what? To these terms. Okay, and so this could be useful to what? To some filter, for example the ECG signal, the biomedical signals. But the hand window, for example, may be created to this one maybe is a biomedical purposes. This one is the encoder or the motor drive purposes, may be useful, these terms. And so our coming signal, which is called to the what? The XT, the input signal, may have different property from each other. In this case we don't have any feedback, but if we are choosing the proper window function, and then we can easily apply the sinc function in here, just like this one. Okay, and so the window function must contain the number of signal as inputs. And also, for example, if we have the n is equals to 5, if we take the measurements at the number of the 500 samples, and so the window function is also as the 500 points. For example, this rectangular window, which is given the n, which means that this n is starting from the what? The 0 to 500. And so this n 0 to 500, 0 to 500. Okay. This is important. Okay. So in the next step, we need to talk about how we can design the FIR filter. First of all, we need to choose the FC, cutoff frequency. Okay. It determines the transition regions. Just remember the Bode plots, guys, between the pass band to stop band, right? Just see that this is the Bode plot, and so we have the filter in here just like this one. This is the transition band. Okay, so this is the what, this is the R flat region, and the other one is the stop band. This stop, this is the pass. Okay, and so in the second case we need to determine the filter length, and the order of filter length is determined by selecting by these things. N is greater, this is the results of this term, if we select the N is higher order, and then we have the sharper transition. For example, if we have the any Bode plot in here, for example, if we choose the N is order of the filter is 10, the other thing is the 100, this is the magnitude, this is the frequency, this is the magnitude and frequency. If we have this kind of transition in here, just like this one, but in the 10 maybe we have this kind of transition region at the frequency range. Okay, and also we need to compute the ideal coefficients, and so in order to do that we need to calculate the sinc function sinc function for desired filter length. Okay, and also we need to apply a window function to convolve these things. Okay, controlling to what side lobes and transition band. Okay, for the selection of the sinc in here for the tree, we can select the sinc function and as equals to the sin n times pi times fc divided by pi dot n. Okay, and also fc should be is normalized frequency, because the theorem dictates us this is the cutoff, normalized cutoff frequency, which is equals to the cutoff frequency divided by sampling frequency divided by 2. Okay, this is the Nyquist criteria, this is the R desired cutoff frequency, and so this should be calculated in here, and so fc is applied in here because the sinc function is in normalized form at this case. Just remember that coming from the proof. Okay, and so we need to solve the example problem in here. So the example can be given by the design fifth order. FIR filter for 250 Hertz. Okay, cutoff frequency with the watt, the fs sampling rate at 2000 Hertz. Okay, and the solution. Firstly, in the step 1, we need to find out the normalized frequency, which is equals to what? FC 250 and 2000 divided by 2, which is equals to what? 0.25. Okay, in the step 2, calculate the ideal response. The ideal response of sinc function. Okay, for the fifth we have the 5 order, or which is equals to n is equals to 5. So the index is r minus 2 to 2, or minus 2, minus 1, 0, 1 and 2. Okay, these are the indices. And the step 2 or 3, calculate the coefficients, which means that the Hn should be built with what? The sinc 0.25 and which is equals to what? The sin pi 0.25 and divided by pi times n. Okay, these are the what? The filter function for a given what? For a given sampling rate and the cutoff frequency. Okay. And step 4, the apply, for example, rectangular window. Like the what? Wn is equals to 1, minus 2 to 2. Okay, which means that this is the simple case, which means that we don't have any effect on signal, right? And so at this case h minus 2 should be built with what? The sinus pi 0.25 and minus 2 divided by pi times minus 2. Okay, and so which is equals to what? 1 divided by 2 dot pi. Okay, and so h minus 1 in the same case 0.25 minus 1 divided by pi minus 1, which is equals to what? The 1 divided by square root times p. Okay, and so h0 can be calculated with what? The sinus 0 divided by 0, which is equals to 1, coming from the what? The limit condition, right? And so this is the what? Is the first coefficient, second coefficient, third coefficients, and h1 can be calculated as the 1 divided by square root 2 pi, and h2 is equals to what? The 1 divided by 2 times pi. Okay, and so this is the simple case for the what? For the designing the FIR filter or calculating the FIR filter coefficients.
for a given the rectangular window in here, because at each case we multiply at the what? At the 1, 1, 1, 1, 1. Okay? And so we have just kind of filters. The n minus 2, minus 1, 0, 1 and 2, and we have this kind of rectangular or the what? The curve like function in here, which is based on the what? The R signals. Okay? And so in the step 5 we need to write to what? I'm writing in here just like this one. Step 5, write the formula in here just like this one. Yn, which is equals to the k is equals to minus 2 to 2 and h k times x and minus k. Okay? So substituting to whole the equations, yn can be obtained with the what? 1 divided by 2 pi times x n plus 2 plus 1 divided by square root pi times x n plus 1 xn times 1 plus 1 divided by square root 2 pi times x n minus 1 and also 1 divided by 2 pi x n minus 2. Okay? This is the generation of the difference equation for the what? For FIR filter design at the rate of the 250 Hertz with the what? With the fs is equal to 200,000 values. Okay? Just remember that we need to create the yn in this in here to what? To apply the xn plus 2, which means that we have the some delay function in here, but we can design this function in order to what? In order to create the linear fuzz, because this is the FIR filter design. Okay? And so apply this function at each step of input coming from the outside. Remember that if we increase n, we have lost the beginning and the end points at the rate of the what? The n divided by 2. Right? Because if we increase the FIR filter up to what? The 50 values, and so we have the x n plus 50 to what? X n minus 50, which means that we cut the first 50 signal in here, just like this one. If this is the x signal, and so this 50 values does not seen in here. The R filter signal is begins with the what? At the what? 50 values. Okay? And so that's all for the what? For the FIR filter design. In the following lesson we will implement the what? The RIIR and the FIR filters on the what? On the MATLAB applications.